for the second time around. Okay, so it says the session is being recorded. So today we're going to talk about integration. We're just actually going to continue on with the area concept. The last time we left off, we were finding the lower sum, the midpoint, and the upper sum, and we were estimating area basically by using rectangles. You'll notice that in one of the homework problems in section 1.1, and as far as the homework is concerned, the homework is open all semester long. So even though it says that for section 1.1 and 1.2, they're both due today, they will actually be open all semester long. Okay. Also, in the section 1.1 homework, I have omitted homework problems 6 through 9. Okay, so those homework problems 6 through 9, those have been omitted from the homework. So even though they appear, you don't have to do them. Okay, this was also a question from section 1.1, and I just wanted to explain this question because it seems like we're jumping from area to distance. So in the last lecture we talked about area. We didn't necessarily talk about distance, but I want to show how what we were doing in the last session and this distance and area are kind of one and the same. So here we're at we're given the velocity, which is the speed or the rate, which is in feet per second in the second column, and we're asked to estimate the total distance traveled during this 6-second interval. So now, how do we actually find the distance when in the last class we were finding the area? Well, if I go back to some geometric terms, the distance is equal to the rate times the time. So if we look at what we're given, we're actually given the velocity, which is the rate. We're given the time, right, which is time. And if we were to multiply those two things together, that actually gives us distance. So how this problem works, I'm actually going to graph this out. Okay, so this is just a rough sketch of a graph. And on the x-axis, I'm going to put time. And on the y-axis, I'm going to put velocity. All right, so if you're following along, I'll give you a second to kind of sketch out what I have. Right, so I'm going to list out the time, 0, 1, 2. Okay, and I'm going to sketch out the velocity. Now, this is just a rough sketch of what's going on. So I'm looking at my numbers. I notice the largest number is 47. So I'm going to kind of label this as 50. So this is about 25. Okay, now I think I'm going to split these things up in half. So I believe this is about 12. And then this should be about 37 or so. All right, so these are just like some ballpark figures. So if I were to plot this first point, 0, 25, I believe that would be about here somewhere. I'm going to plot my second point, 1, 45, which is about here. 2, 47, 3, 28, 4, 7, 5, 2, and 6, 18. Okay, so the graph looks basically something like this. All right, so here again, this is just a rough sketch. Right, so what we're asked to find is we're asked to find the distance. We're asked to estimate the distance of the line. All right. So one thing that's not actually given in the directions, we're using the left endpoint. Okay, for whatever reason, part of the question got chopped off. All right, so if we're using the left endpoint, I'm using the leftmost number as the height of my rectangle. All right. So now it's not really giving us a number of rectangles. So notice we're going in 6 seconds. So I'm going to use a width of 1 for each one of my rectangles. So for my first rectangle, right, it's going to be on this first interval from 0 to 1. All right, and I'm simply using 1 because they're giving me 1 second intervals. I'm going to use the height as a left endpoint, which is 25. For my second rectangle, it's on the interval from 1 to 45, and it's going to have the height of 45, which is the left endpoint. Okay. And then so on and so forth. So this is going to be R3. So notice in this problem, we're not really using an upper sum or a lower sum. We're using the left endpoint. I'm going to just sketch the rest of these things out. This is R5 and then R6. All right, so I'm sketching out my rectangles. So now this is where the distance comes in. If we multiply the rate times the time, that actually gives me the area, but in this case, that area is actually the distance. So I'm simply going to find the areas for all 6 of my rectangles, which is inadvertently the distance. I'm going to add them all up to give me the total distance. So keep in mind that for each one of these rectangles, the width is 1. So for the distance, I'm going to multiply for my first rectangle, my width, which is 1, times my height, which is 25. For my second rectangle, I'm going to multiply my time, which is 1, times my height or my speed, which is 45. For rectangle 3, here again, the time times the rate, which is 47. And if I repeat this process, and if I add up all of those numbers, I believe I would get 154. Right, so the distance traveled would be 154 feet. All right, so I believe that was problem number 4. Okay, so we're finding basically the area of these rectangles, but for these rectangles, our dimensions are the rate and the time, which actually gives us the distance. All right, so this is approximate distance. All right, now we'll actually talk about the setup for integration. And I'm going to navigate to the shared screen. So hopefully, wrong way. All right, so I'm actually going to go into those lecture notes, and I'm going to go back into that section 5.1 through 5.3 set of notes. All right, and we're going to talk about, I'm actually skipping over 5.2 momentarily. All right, and we're going to talk about the definite integral. All right, so this is the setup for integration. So basically, we're going to take what we were doing by using the rectangles, and we're going to use some formulas in this session. We're going to set up what's called the integral or integration. So here we have this S-shaped symbol, which is the integral symbol. So remember that integration is area. So we have the integral from A to B. A would be our lower limit of integration. B is our upper limit of integration for f of x dx. Now, f of x, that's your function. D of x, or x, is the variable of integration. Keep in mind that every integral must carry a variable of integration. In this class, we're going to integrate on both the x and the y-axis. All right, so our integral symbols are either going to carry a dx or a dy. We also have what's called infinite integrals, and infinite integrals do not carry limits of integration. But before we talk about those infinite integrals, we're going to talk about definite integrals. All right, so I'm going to go back to the shared screen, and we're going to see how we can use integration to find area. All right, so in order to explain integration, I'm going to start out by using some classical geometry and some classical geometric formula. So I'm going to take this function, y is equal to 2x, and I'm going to graph it. All right, and I'm going to graph it just using a basic x and a y chart. Right, normally when you make an x and a y chart, you should use the negative numbers, you should use 0 and a positive number. So I'm going to use -1, 0, +1. And I'm going to substitute into the formula. So if I substitute x for -1, 2 times -1 is -2. If I substitute x for 0, I get 0. If I substitute in a 1, 2 times 1 is 2, I get 2. So I have a set of ordered pairs, right? And I can plot these ordered pairs. I'm actually going out to 4 in this, so 1, 2, 3, 4. So if I were to just put those in, I think you can see this. I believe I'm going to have 4, 6, and 8. All right. So if I'm going to plot that, the line should look something like this. That'll be y is equal to 2x. And this is mainly what I'm concerned in. All right. All right. So this is basically what I have. I'm going to restrict this domain at 4, right? From 0 to 4. And this is going to produce a triangle, right? And what I want to do is I want to find the area for this triangle. All right, so if I kind of take everything away, you know, the 2x and the x and the y line graph, I know a couple things. I know that my base is 4. And my height is 8. Right? So if I were to use a classical geometric formula, the formula for the area of a triangle is 1/2 the base times the height. I know that my base is 4. My height is 8. So I get an area of 16 units squared. Okay, so this is using the classical geometric formula. Now, how could I use, so I'm just going to label this as classic geometry. So now how can I use integration? All right, because integration is the area under curve. So first off, I need an integral symbol, and I need limits of integration. Since we're integrating on the x-axis, I'm going to use the x, my domain, as my upper and my lower limits. So here, we're integrating on the x-axis from 0 to 4, so my lower limit is 0. My upper limit is 4. I also need a function. So notice that we had an integral from a to b for f of x dx. So what's my function? Well, my function here is 2x. Since I'm integrating on the x-axis, dx. Okay, so this is the setup for my integral. So now how do I integrate it? Well, now integration in this class is sort of twofold. There are some area formulas to integrate it. So when I say area formulas, you know, we have these classic geometry formulas, but there's also some area formulas for integration. And then we have what are called the integration formulas. First, I'm going to start off integrating this by using what are called the area formulas. All right, so I'm going to go back to the shared screen for just 1 second. And if I go into the formula sheet section of the course, I just want to show you where these formulas are coming from. I want to go into this area formulas link. And here we actually have, I believe there are 3 formulas. And this is the first formula. It says the integral from a to b for x dx is equal to b squared divided by 2 minus a squared divided by 2. All right. We also have the integral from a to b for c dx. So notice in this integral, this is just a constant. That would equal to c times b minus a. Next, we have the integral for a to b for x squared. That's equal to b cubed divided by 3 minus a cubed divided by 3. Since our problem deals with x raised to the first power, this is the formula that we're going to use. All right, so this is the integral from a to b for x dx is equal to b squared over 2 minus a squared over 2. All right, so I'm going to go back to our document camera. All right, and we're going to use that formula here. Okay, so we're going to use that formula here. All right, so this was the formula, the integral for x, the integral from a to b for x dx. That was equal to b squared over 2 minus a squared over 2. And we're asked to integrate from 0 to 4 2x dx. Okay. So the first thing I'm going to do is pull this constant in front of the integral operator. All right, so notice in order to use this formula, I must specifically integrate x to the first power, right? The coefficient is understood 1. So I'm going to pull 2 in front of the integral operator. And now I'm going to use a formula. So remember that we still have 2 on the outside. So the formula said it's b squared divided by 2. So b is 4. So we have 4 squared divided by 2 minus a squared divided by 2. So a is 0. All right, so that equals to 2 times 16 over 2. The 2's cancel, so we have 16 square units, right? Which is the same result we got from our classical geometry formula. Right, so any questions about using this formula? Now, a little bit later, we'll actually use some integration formulas, but from the onset, we're going to look at those main 3 formulas. This is the formula to integrate x. There's a formula to integrate x squared, and there's also a formula to integrate a constant. We'll also take a look at a third way to integrate. And this is by using a calculator. Okay. So we're going to integrate the 2x from 0 to 4, but in this instance, we're going to use a calculator. So now, even though I'm using a TI-83, if you're using a TI-84 or a TI-84 Plus, you should see the exact same keystrokes. So I'm going to go into Math, and within Math, I'm going to scroll down, and I have FNINT, which is function integration. Now, when you use your function integration, it requires 4 parameters. You must put in your function. So our function is 2x. I'm going to put in a comma. You have to put in the variable of integration, which is x. You must put in the variable of integration. Then you put in your lower limit. You want to put in your upper limit. And it gives us the integral of 16. Now, you can only use the calculator for definite integrals. Okay, you must put in a lower limit and you must put in an upper limit. All right, so we just looked at, I guess, 3 ways to integrate. You can integrate by using a classical formula if possible. You can integrate by using the area formulas. You can also use a calculator. Okay. All right, I'm going to go back to our document camera. All right, and I want to take a look at this problem. All right, and you'll see a problem, I believe there's a problem similar to this in the section 1.2 homework. All right, and you will be asked to find the distance traveled. So here again, this is the distance versus the area sort of thing. So notice the layout. We have the time on one axis and the velocity or the rate on another axis. So if we were to subdivide this into 5 regions, And if we could find the area for each reason, right, that time times the speed would actually give us the distance. Okay. So now for this problem, since this is not a classical shape in itself, if I'm looking at it as a whole, I can't necessarily use the geometric formulas. I can't necessarily use an integral formula, right? Because the integral formulas we've learned up to this point are for the x to the first power, and if you were to grab x to the first power, that's simply a linear function. There's a formula to an area formula to integrate x squared, so x squared would give you U-shaped graphs or parabolas, and this is neither one. So what we'll do in order to find the distance for this problem is we're going to subdivide this region into 5 shapes. Okay. So I'm going to look at this first region from 0 to 1, and I'm going to treat this as a shape. And that shape would be a trapezoid. So let me explain a trapezoid. For a trapezoid, it's a 4-sided figure. 2 of the sides are parallel. All right. These 2 parallel sides are called the bases. Remember that from geometry, 2 lines are parallel if they never touch. So this is my little b or little base. This is my big B or big base. And then you're going to have the other sides which are not parallel. All right, so a trapezoid can look a bunch of different ways. It can look like this. All right. And if our trapezoid looks like this, I'm actually given the height. So here's the formula to find the area of a trapezoid. The area of a trapezoid is equal to 1/2 the big base plus the little base times the height. And that would give me my area. All right, so remember, a trapezoid has 2 parallel sides. Those parallel sides are the bases. All right, so I'm actually going to use that here. Right, if I look at my first figure, right, this is actually a trapezoid. Right, if I turn it on its side, this would be my little base, which would have a length of 4. This would be my big base, which would have a length of 5. And my height is going to be 1. So I'm going to call this area 1, right? So inadvertently, I'm finding the distance because the time times the rate is the distance. So I'm going to change this to D1. So the distance in that first interval, that's equal to, and that's a trapezoid, so it's 1/2 the big base plus the little base times the height, which is 1. So I get 9/2. For my second distance, I'm going to call this D2. Notice I have a rectangle. And for this rectangle, I can simply multiply my time times my velocity, or my width times my height. So my width is 1, the height is 5. So I have a distance of 5. Oh, let's do that. So I have a distance of 5, right? For my third distance, if I turn this on its side, notice that this is a trapezoid. I have 2 parallel sides. So my big base is 5. My little base is 1. And the height is still 1. So for that third distance is 1/2 5 plus 1 times the height, which is 1. So that's going to give us 3. For D4, if I turn that on its side, notice that that's again a trapezoid. So my little base is 1. My big base is 5. The height is still 1. So that fourth distance is 1/2 5 plus 1 times the understood 1, which is the height. And then the same thing for the fifth distance, D5. Again, that's a trapezoid. My big base is 5. My little base is 1. My height is 1. So now if I add all of those things up, 9/2 plus 5 plus 3 plus 3 plus 3, you should get 37/2 as the distance traveled. All right, so notice that here again, for those distance problems, you're still multiplying width times height, but it's a special width, which is the time, and a special height, which is the velocity, which in essence give you the distance. Okay, and the last thing we're going to do for today, we'll take a look at some properties for integrals. So if I go back to some of the properties or the rules for definite integrals, here's some basic rules. If you reverse the order of your limits, so notice this thing reads as the integral from a to b for f of x dx, that's equal negative from b to a f of x dx. If you reverse the order of your limits, you must multiply your integral by a negative. So that's simply what this means. Let's say if this were the integral from 6 to 0, f of x dx was equal to 5. If I were to reverse those limits, that integral will be equal to -5. Okay, so we'll take a look at that in a second. There's a 0 with interval. It says that the integral from a to a for f of x dx is equal to 0. So if your width is 0, so notice that if my upper limit and my lower limit are exactly the same, I have no width for my rectangle. then that's a 0 with interval, and the value of that integral is 0. There's a constant multiple rule, which we saw earlier. The constant multiple rule says you can take any constants and pull them in front of the integral operators. So when we integrated 2x dx, we pulled 2, which was the constant, in front of the integral operator. There's a sum and difference rule, and the sum and difference rule says that the integral from a to b for f of x plus or minus g of x dx, you can distribute your integral, right? Just as you can distribute using the distributive property, you can distribute this integral. So you can distribute the integral as the integral from a to b for f of x dx plus or minus the integral from a to b of gx dx. So you can distribute the integral. The key thing here, though, is this additivity. And the additivity rule says that the integral from a to b for f of x dx plus the integral from b to c for f of x dx is equal to the integral from a to c of f of x dx. To get a visual example of the additivity rule, okay, it's a little bit better here because we can actually see what's going on. So what this thing says is, if you were to add up this integral on the interval from a to b, right, so that's the first part, plus the integral from b to c, that's the second part, that's going to equal the integral from a to c for your function f of x dx. So that means that you can add limits. So here's an example. Okay, for this example, notice that I'm given two facts. My first fact is the integral from 0 to 5 for f of x dx is equal to -5. Okay, so it's really not giving me what my function is per se, but it's giving me that it's f of x dx. I'm also given the lower limit, which is 0, the upper limit, which is 5, and I'm also given that area, which is -5. And the integral from 0 to 2 for f of x dx should equal to 6. So these are two facts that I'm given. I'm asked to find the integral from 2 to 5 f of x dx. All right, so how do I find the integral from 2 to 5 of f of x dx? I'm only given the integral from 0 to 5 and the integral from 0 to 2. All right, so here's where that additivity rule comes in. The integral from 0 to 2 for f of x dx plus the integral from 2 to 5 for f of x dx should equal the integral from 0 to 5 for f of x dx. All right. So based on that additivity rule that we just saw, I'm going to try to sketch this out. So let's say here we have a 2, excuse me, we have a 0, a 2, and a 5. So from 0 to 2, for f of x dx, we have 6. The integral from 2 to 5 for f of x dx, that's unknown. But the integral from 0 to 5, which is this entire region, is -5. So I'm setting it up like an algebraic formula. The integral from 0 to 2 for f of x dx plus the integral from 2 to 5 for f of x dx should equal the integral from 0 to 5 for f of x dx. So now I'm simply just going to substitute in the values. So the integral from 0 to 2 for f of x dx, that was given as 6 plus the integral from 2 to 5 for f of x dx, that's our unknown. So I'm simply going to write the integral from 2 to 5 for f of x dx. But if I add these two things together, I should get -5. And now I'm simply going to solve it. I want to subtract 6 from both sides. So the integral from 2 to 5 for f of x dx should equal to -11. All right, so now I want to jump to one last problem. I'm going to go back to our application screen. All right, and I just want to point out a couple things. In this section 1.1 homework, problem number 6, 7, 8, and 9, you want to just omit those. I tried to take them out, but I believe once the homework was opened, you can't go back in. Well, anyway, these problems kind of deal with 30 and 40 rectangles, okay, which is a little bit absurd to do. So I have taken those 4 problems out. Everything in the section 1.2 homework looks to be just about right. Even though these assignments are set to be due at 11:59, they still will remain open after the due date. Okay, the next time we meet, we'll talk about something called marginal cost. There are a couple of those business related type problems that pop up about marginal cost, revenue, profit, and that sort of thing. All right, so I'm going to stop the recording for today.